So let us discuss with the main part of number theory, that is unit 2, which is defined as topic is linear concurrence. So how we define it? It is defined as if you have let a, b, m be integers with the condition that a is not concurrent to 0 mod m, means that a here is not a minus 0 here is not divisible by m, or m does not divide a, and x is any unknown solution, then the concurrence ax concurrent to b mod m is called a linear concurrence modulo m. So you just recall the definition of concurrence here is that if a is concurrent to b mod m, if and only if m divides a minus b. So if and only if m divides a minus b here, it implies that by definition of divisibility, a minus b can be written as m into k, a multiple of m, or if and only if a minus b or a is equal to b plus m k, or if and only if you can write it back to this, we can say that a is concurrent to b mod m. So for example, we wish to solve the linear concurrence 3x concurrent to 1 mod 5, and in this solution, if the solution in this case there are infinitely many numbers which satisfy this linear concurrence 3x concurrent to 1 mod 5. For example, you take x equal to 2, x equal to 2, x equal to 7, x equal to 12, and from the negative side, for example, if you take x is equal to 2, so 3 into 2 here is 6. 6 minus 1 is equal to 5, which is divisible by 5. Based on this definition, a is concurrent to b mod m if and if m divides a minus b. So if you replace x here by 2, so 3 into 2 is 6. 6 minus 1 here is equal to 5, which is divisible by 5. So therefore, similarly, by replacing x is equal to 7, 12, and from the negative side also, so therefore the solution will be of the form, this one, x equal to 5k plus 2, where k is an integer. K here you can take it equal to 0. The general solution for this 3x concurrent to 1 mod 5 is by taking k to be any integers, it will be of the form 5k plus 2. So from here you have 5k plus 2, k is positive integer from 0, 1, 2, 3, you will get the solution 2, 7, 12, and so on. From k is negative, you will get this solution, and so on. So therefore, it makes sense to consider the solution of the concurrence to be of the, or you can write here, x is equal to 5k plus 2 can be written as x concurrent to 2 mod 5. How? X is equal to 5k plus 2, or you can write it as x minus 2 is equal to 5k. X equal to 5k plus 2, or you can write it as x minus 2 is equal to 5k if and only if this one 5 divide x, if and only if you can write here this one 5x minus 2 is a multiple of 5, means 5 divides x minus 2, or you can write x minus 2 is equal to 5k, so which is of this form. So from here, this implies that x is concurrent to 2 mod 5. So, or you can go back from here, x concurrent to 2 mod 5 implies that x here is equal to 2 plus 5k, implies that x minus 2 is equal to 5k, implies that 5 divides x minus 2. So therefore, in general, it makes sense to consider the solution of this 3x concurrent to 1 mod 5 as x. Any x which is concurrent to 2 mod 5 will be a solution of this 3x concurrent to 1 mod 5. Similarly, x concurrent to 7 mod 5 also will be a solution of the above linear concurrence 3x concurrent to 1 mod 5, and so on. But the smallest among this is 2 by taking x concurrent to 2, because so therefore 2 here is called the least positive residue. So in general, the solution of the linear concurrence ax concurrent to b mod m, if it exists, will be of the form x concurrent to t mod m, where t here is the least positive residue modulo m. By least positive residue modulo m we have here, you take any b to be an integer, and m is a natural number. Natural number, it means that it is a positive integer, starts from 1, 2, 3, and so on. And when you divide b by m, then by division algorithm there exists quotient cubed and remainder are such that b can be expressed in the form of m cubed plus r, where r here is greater than or equal 0 but less than or equal to m minus 1, and m being the divisor here. then we say that this R, that is remainder, is called the least positive residue of this B. So now let us come to the main theorem of this linear concurrence and how it states that it is an important theorem. Consider the concurrence AX concurrent to B mod M. Then the concurrence, this linear concurrence, has a solution if and if the GCD of A and M divides B. Number 2, if U naught is any solution of this linear concurrence AX concurrent to B mod M, then the complete set of solutions are U naught. They are of the form U naught plus M by G, U naught plus 2M by G dash dash, U naught plus G minus 1 M by G, where G here stands for the GCD of A and M. Thus, there are G solution. If you count from here 1, 2, 3 up to G minus 1, you will get G solution. And number 3 is a particular solution U naught can be obtained by solving the concurrence A by B upon X into X is concurrent to B upon G into modulo M. And this is possible since the GCD of A by G and M by G is equal to 1. This will refer from unit 1. I have already discussed, given you the properties on GCD and concurrence. So let us prove the first part. What does it state? Is that suppose here GCD, suppose the linear concurrence AX concurrent to B mod M, because it is an if and only if statement, has a solution, say U belong to the set of integers, that is AU is concurrent to B mod M. So AU concurrent to B mod M here implies that M divides AU minus B according to the definition of concurrence A concurrent to B mod M if and if M divides A minus B. Now since G here is a GCD of A and M, so it implies that by definition of GCD, G is the common divisor of A and M, implies that G divides A and G divides M. And from here, AU concurrent to B mod M, it implies that M divides AU minus B. And from G divides A, it implies that A here is equal, A is a multiple of G, that is A, G into K for some K belong to Z. Now multiply this both side by U, so you have AU is equal to GK into U. Or you can, this still implies that G divides AU, or you can say that AU is a multiple of G. You refer all this from the definition of from the basic properties of divisibility. Now M divides AU minus B and G divides M. See, M divides AU minus B and G divides M, since it is a GCD of A and M. It implies that G divides the difference of these two. G divides M, so it implies that G divides M and M divides this. So if you have A divides B and B divides C, from one of the basic properties of divisibility, it implies that A also divides C. Now M divides AU minus B and G divides M, it implies that G will divide AU minus B. So write this as equation 1 and this as equation 2. So if G divides A, if M divides A and M divides B, it implies that M divides a difference or plus or minus B. So using 1 and 2, it implies that G divides the difference of this AU minus of AU minus B. AU and AU can be cancelled. So minus into minus plus, it implies that G divides B. Thus the linear concurrence, if AX concurrent to B mod M has a solution, then it always implies that G divides B. Conversely is, suppose G divides B, what we need to show is that the linear concurrence AX concurrent to B mod M has a solution, where G here stands for the GCD of A and M. So if G is a GCD of A and M, from the basic properties of linear concurrence, it implies here if G is a GCD of A and M, it implies that their axes R and S belong to set such that G can always be expressed as a linear combination of A and M, that is AR plus MS. You refer to one of the basic properties of GCD. So here also using that properties, this one, there exists R and S such that G can be expressed as a linear combination of A and M, that is AR plus MS. Now AR plus MS is equal to G. Multiply on both sides of this by B. You have ARB plus MSB is equal to G into B. Now after that, you divide both sides of this equation by G. When you divide it by G, you have ARB by G plus ms into b by g is equal to b. This makes sense because b by g is an integer. Why? Because g divides b. Had it not been, that means if g does not divide b, this is not possible. But since g divides b means g divides b, it implies that there exists integer k belong to set such that b can be expressed as g into k, or you can say that b by g is equal to k, which is an integer. So that's why we can divide it by g on both sides. So this implies that rearrange them, or you can write here ar into b by g is equal to b minus, when you bring this to this side, you get minus m into b by g, ms b by g. Or you can write here a into rb by g is equal to b plus m that plus, you write plus here, and this minus sign you write it here, m into minus sb by g. And from here you compare it with the definition of divisibility. If a r b by g is equal to b plus m into sb by g, it means that m will divide the difference of this a r b by g minus b, or we can say that a r b by g is concurrent to b mod m using this definition. M divides a minus b if and if a minus b is equal to mk, if and if a is equal to b plus mk, or if and if a is concurrent to b mod m. So this is if and only if. I'm using this from here, from this step, as you can see here, this part here, it implies that a is concurrent to b mod m. So I can write here a into rb by g is concurrent to b mod m using this definition of the concurrences and divisibility. So from here it implies that, so as you can see that a into rb by g is concurrent to rb by g is concurrent to b mod m. So you just replace x here by rb upon g. It implies that the linear concurrence ax is concurrent to b mod m, or we can say that if g divides b, then x equal to rb by g will be a solution of the linear concurrence ax concurrent to b mod m. So this completes the first part of the proof of the first part of the theorem. So in the next video we will discuss the second and the third part of the theorem. If anything is not clear from here, you just inform me which part it is not clear to you, then we can discuss it again. Okay, so therefore for the first part I have completed. So in the next video we'll discuss the second and the third part of the theorem.